Okay, so I'll give you a little presentation today about my some of the work I've been up to over the last couple years. For my PhD, I originally started with a project that was funded by the U.S. Forest Service. I'm going to start by telling you about some of the projects I worked on that I'm not planning to do my dissertation on. And I've got this crazy pie in the sky one that I'm going to present to you today. And if you're like, yeah, no, then I'll go with one of the other ones. That's basically the idea that I've got in my head here. So I'm hoping that you can kind of give me a little bit of a gauge of what you think. So anyway, when I got started with the PhD program, I was part of a group that was funded by the U.S. Forest Service because we're about a billion board feet a year short of lumber in the United States, and they really don't like importing it from Canada and other places. And so the research was to find ways to economically recover wood and other materials from existing buildings that, would be deconstructed. So the economic analysis that was done basically suggested that deconstructing the home with manual labor did not make anybody any money. It was a money loser, right? It was much cheaper just to tear the building down, dump it in the landfill. But some of you may know that 40 to 50% of landfill waste is construction waste. It's like almost half, right? So it's a big problem. We actually deconstructed some houses as part of this research. It's a huge pain in the butt to try to pull nails and all that other stuff out of wood. So we started prototyping various technologies to detect material in wood and find ways to mechanically separate and remove it. And so I created this design here, and we use all kinds of different technologies, ultrasound and vibration, various vibration technologies. And this was here an example of MRI. So we actually used an MRI machine, and you can set different wavelengths in the MRI to find things like lead. So that was that. We wrote the paper. I know some of you might have seen it. I think I was talking to Larry maybe. George Berghorn, who some of you know, was the lead on that one. And some company, I can't remember the name of the company, but they ended up buying the technology, and I kind of bowed out of the whole project. So I'm still on the Slack team. I can kind of see updates here and there when I feel like it, but it just wasn't really that interesting to me. There's another group that I just saw their paper. What their project was, which I think is a better idea, is pulping down all the wood and then reforming it into new wooden forms with some kind of chemical additives or something like that. I think that's probably way easier than trying to mechanically pull out nails and all this other stuff with computer vision. But anyway, the other area that I've been doing a lot of research in is the 3D printing in buildings, for buildings, of buildings. I'm not really sure how you want to describe it. This isn't my work or anything. This is just, I have a lot of random pictures I stole from the internet for this presentation, by the way. So right now with the way that the technology is, everybody thinks about 3D printing for construction for buildings in terms of using the 3D printing technology to build the building. And I'm of a completely different mindset on that. So, this is an example here of a little 3D printed home. I think the biggest they've done so far is like a 4-story apartment complex in China. That's all great and everything, but I think personally about all the other stuff that goes into a construction project. So I've spent the last few summers working on construction projects, and it comes up all the time that your little parts and pieces and all kinds of little stuff that's missing. And I think there's some room for innovation there. These are all easily printable parts here. So over the last several years, I got started in 3D printing in 2011, built my own machine off of some Kauffman Foundation grant money, and I've been hooked on it ever since. This is one of my first projects that I did. I started making gears for people. So I started with just regular thermoplastics, eventually was able to get into like metals and carbon fibers and stuff like that. So some of these gears are still in machines today. My last job was for a carpenter, like a guy that owns like a furniture shop, and he had a bunch of Delta equipment. Delta went out of business. He can't get the parts anymore. So I was able to scan and print some gears. Done some prototypes with flooring, 3D printed flooring. We dropped a little decoration into some cement there. That's not the finished product. I didn't get a chance to take a picture. They covered it in like epoxy and all that stuff and shined it up. Had a gang box lock go bad. Replaced one of those with carbon fiber. And probably the biggest one I've done so far. This isn't all of the ones I've done, but probably the coolest one was the shower door hinge. It was a 200-unit apartment complex, and the shower doors got sent over from China, but they forgot the boxes of the little acrylic hinge pins that go in there. And so I printed 400 and some of these pins in about a 2-3 day time period, and installed them all. So yeah, stuff like that. This one was from some architect who was having a problem. They were laying down these, epoxy resin poured floors, and they were having a lot of problems with like clumpiness and bubbles. And so I prototyped a bunch of these like strainers, and until we got the right kind of size of hole, and that they pour that through the strainer, and then kind of shift it around the floor. So that's some of the stuff that I've been doing. I have a feeling like with the way that 3D printing is going, the way the construction industry is going, I think we can, I think there's going to be a time when manufacturing some of the stuff right on site while the building is going up might make sense. For instance, with this flooring here, one of the things I've been thinking about doing is basically attaching a 3D printer to a Roomba, and just having it, put down flooring as, after everybody leaves the building. So, yeah, those are some of the ideas that I've been working on. So, yeah.
I know this isn't your main part of the presentation.
Yeah.
Out of curiosity, for your metal printing, are you using metal powder and then baking it, or?
It's more or less like welding, really.
More technician style?
Yeah. Yep. It's high temp, but not like those powder machines are. I can't get into that price range. But yeah, it's amazing what the technology's done in just the last few years. It's pretty incredible. So yeah, if you got comments or questions, just jump in, just interrupt as I go. All right, so the main thing I'm here to talk about today is we'll call it systems thinking, Bob. We'll call it systems thinking. It might be off the rail system thinking, but nonetheless, here we are. So air pollution, big problem, right? To date, air pollution, both ambient, outdoor, and indoor, is the biggest environmental risk to health, carrying responsibility for about 1 in 9 deaths annually. Some picture I found. So this is the US AQI levels here for PM 2.5. You're about to see a lot of red and purple, a little bit of orange areas in some of these maps I'm going to show you. But generally speaking, a lot of places in the world are in this range here, and not so much in this range here. If you live in an urban environment, you're at least in the United States, you're at least here, if not in here. So this is back from November of 21.
What
Yeah.
kind of pollutants are we seeing there?
PM 2.5.
But what is it? Particulates or?
Yep, particulates,
Toluene or?
all of that, yep. Benzene, right, SOx and NOx, all that kind of stuff, yep. So in November, it's a bad time of year, especially if you're in India, because they do a lot of what they call stubble burning. So the farmers basically burn down their, after they've harvested their crops, and then all of that smoke ends up going through the major urban centers in India and other countries that have similar farming practices. So you can see here how high they get, right? We're in that very unhealthy range. General public will be noticeably affected. Sensitive groups should restrict outdoor activities. I can tell you personally, when I went to Beijing in 2008, it was here, right? And I was like in my 20s, and it was hard to breathe. It took me 3 or 4 weeks after I got back from China for my lungs to feel like they healed. It was like I just became a chain smoker for a semester. It was tough. So yeah, here we go. This is the worst in the world in 2021. Here's where I live, right here in Lansing. This is today, and we have a 500 dot right here. I don't know what happened, what set that off, but as you can see here, we are in this range here, right? And that's just a few miles from where I live. So this is not a problem that just exists some faraway place. Detroit, typically, this is Dearborn's just outside of Detroit. It's about right here. Typically gets up pretty high. We have notices on our radio and TV from time to time that tell us, don't go outside, avoid strenuous activity. If you do go outside, wear a mask, all that kind of stuff. So this was yesterday. Delhi, India, off the charts, right? It says here PM 2.5 in Detroit currently 3.6 times above the WHO annual air quality guideline, right? So Detroit is 26 in the world. Again, this was taken yesterday, right?
Could you flip back there 1 second?
Yeah.
Look at Mexico City there.
Yeah. Yeah.
Unbelievable.
Yep. Really bad.
They got bad plumbing, Peter.
Well,
So yeah, based on the model data, 92% of the world population are exposed to PM 2.5 air pollution concentrations that are above the mean AQG levels of the 10 nanograms per cubic meter, right? So this one makes it look like North America is not doing so bad, right? Because of the way the gradients are drawn. But when you look at something like this one here, it kind of gives you a little bit more resolution, we'll say. All these little things that you see here, coal-fired power plants, that's what all these little symbols are here. So clearly this is the area of the country here that really struggles with air quality issues. All right, so I got a kick out of this from, I think it was the UN website. How can I improve air quality in my home, right? It says here, if the air pollution levels are already exceedingly high, wear a mask in your own home. They also recommend this in like when they have the fires in Florida and all that kind of stuff. Obviously, it's getting pretty bad, right? All right, so about 30% of global expenditures go to healthcare. That's $2.6 trillion annually. In the United States, it's $790 billion. That's 5% of GDP. 197,000 deaths per year from air pollution. And I got a kick out of this one here. Despite having the most expensive healthcare system, the United States rates last overall compared with 6 other industrialized countries that you can see there. So yeah, we're not doing so great here in the United States. All right, so where does the pollution come from, Peter? It comes from coal ash, SOx and NOx, mercury, cadmium, arsenic, et cetera, et cetera. 40% of waterways are unsafe to use for fishing or swimming. I know this personally because I like to fish. It's really the only form of like hunting that I'm able to do. I take my kids quite often, and we get a guide at the beginning of every fishing season that tells us which waterways we can fish in and which fish we can pull out of there safely. And it makes me really sad that that's where we've gone. We also have about 20,000 tons a year of radioactive thorium and uranium. About 1% of that escapes into the air. All right, so how do we solve these kind of problems, right? So AQI, air quality index, IAQ, indoor air quality, right? So, if we want to solve this air quality index problem, we need to, reduce our consumption of coal, we'll say, right? We need to, reduce the amount of pollution that we're putting in the air. We need to move to more clean power generation using electrostatic precipitators, scrubbers. This is not, for many of you, is not new information. Obviously convert to renewable energy. On the IAQ side of things, people spend 90% of their lives indoors on average. So over the last 100 years, we've seen a major shift from basically everyone working outside to nearly everyone working inside. Many across the world still burn fuels indoors for heat and cooking. And so, we need to address that through air filtration and ventilation. I don't know if you noticed, but you keep seeing this word pop up here, maybe. Move a lot of air. Move a lot of air. So, one idea that's been attempted is to filter outside air. This is in China. Other places where something like this, may be helpful would be in India, possibly the California wildfires, right? Something along these lines here. I think this is kind of hokey, but they're trying something, right? All right, so to summarize that section, goal number one, we need to do something about our air pollution problem, right? We're all breathing really, really bad air. Human health crisis costs trillions of dollars, reduced quality of life, negative impact on the global economy. So we need to do something about our energy production and how we treat indoor environments. And yeah, the United States is probably a little on the higher end than, say, somewhere like India. All right, now next we're going to talk about the power generation industry. Electricity demand is expected to grow 4% per year. Agriculture is being highly automated, right? So we're seeing a lot of electrification of the agriculture industry. So this commercial and residential here, this 13%, that's mostly having to do with burning of like natural gas, propane, fuels, things like that. Of course, in our industry, there's a big move to switch to heat pumps to do electrification. In the transportation industry, we're moving to electrification as well to do electric cars. In industry here, a lot of big industrial plants have their own power plants on site, and they're going to do whatever's cheapest, which is going to be burning wood, burning coal, whatever they can throw at it. All right, so electricity consumption for commercial buildings, 41% of that is the HVAC, biggest load. If you go to residential, it's almost half. It's like half the load, right? Makes sense. Industry, almost 30%. Still the largest chunk, except for maybe that machine drive, like the main part of their, operation. All right, so the power generation.
On that last graph, Sean,
Yeah.
on the industrial side, do you know if that big chunk for their main process, is that including any industrial cooling that might,
There's process cooling in there, 8.4.
Yeah.
okay, cool, I just couldn't see it from here. Thank you.
I have a question.
Yeah.
How does the power consumption from electric cars get into all these graphs? All the electric vehicles?
Oh, yeah.
Same as all.
So I'm going to guess it's probably in this part of the pie here. I mean, this is from 2019. I don't know what's the percent of electric cars out there? 2%, 5%? I'm not sure. It's got to be pretty small.
Because, if they keep going and wanting to build more electric vehicles,
Yeah,
they have to generate more power.
correct.
Where is that ultimately going to come from?
Rays of sunshine.
Yeah, I don't think so.
Well, that's solar, man, come on.
No, I don't think that's going to happen.
Yeah.
A very big question.
Well, it
Unless we
is
start
the question, and I think that,
building a lot more.
we have actually seen a lot of change there. I mean, 10 years ago, we're up to 18% from in solar. That's huge. That over a very short period of time. I mean, that's where a lot of it's going to come from, and it's going to take time, and it's going to take developing the storage, because as you know, we can't just do things when the sun's out.
Right.
That's where it's going. Right now, that's about all we got.
Well, the whole lithium mining, and then once the batteries die, where are they going to?
No, well, batteries are pretty recyclable, but yeah, peak lithium is on its way. Yeah, what you got?
Back in 2019, I was doing it. I'm driving EVs, charging it with the solar,
Yeah.
renewable, and it's net zero now.
Absolutely. You have panels on your roof? Yeah, I took mine down in 2018, put a new roof on, and I'm hoping to get panels back up on my roof this year. So we'll see. I'm a little busy. Yeah, so again, preaching a lot of this stuff is preaching to the choir. I know you know a lot of this stuff. So current transmission is I mean 33% efficient is what they say. I think it's less than that when when you really have a look at it. Biggest consumer of power is HVAC. We're the biggest ones. You guys know this one: carbon dioxide concentrations, right, off the charts. You know about this one. So yeah, energy-related CO2 emissions. Oil's still our biggest.
You know one back real quick?
Yeah,
Was that
you know the hockey stick, right? But this one here at least is set to expand, right? Unless we do something, unless we get off of coal. We're moving to this economy. At least this is what it looks like to me. That we're going to try to move away from natural gas. We're going to try to move away from oil. Yeah.
You said that a couple of times now, and I just went to Wisconsin,
Yeah.
forum about our
Yeah.
utilities,
Uh-huh.
and they're totally beefing up natural gas in our state. and
Yeah,
they
yeah.
take down coal plants.
Yeah.
So I'm wondering if that's just like a regional thing. in
West
Wisconsin.
Coast,
Is it the West Coast?
yeah,
that's-
California, Washington, Oregon.
They're
Can you
taking out
repeat
natural gas.
What Jen is saying?
What are they gonna replace it with?
Oh, that some of the coal power is being replaced by natural gas.
Yeah, well,
We have the same in Michigan, where I live in Lansing. We have a cogen plant that's barely 3-4 years old, so it can accept biomass, natural gas, right? It's able to work under different combustion scenarios. Same thing at Michigan State University. We got off of coal about 4 or 5 years ago, and they have a cogen plant as well. Largest university-based power plant in the country. So, but yeah, a lot of solar panels as well on that grid. Yeah.
One of the problems with natural gas is that there's a lot of methane leakage,
Correct.
and it's really much, much worse than carbon dioxide, although it gets out of the atmosphere faster.
It's like 4 times, I think I might have a slide on that. It's like 4 times worse than CO2 emissions. It does kind of look like, from a regulatory standpoint, we're hunting and pecking, trying to figure out what's going to work and what regulators can stomach.
And the scary thing is that I read 2 articles that scientists were pointing towards nuclear energy as being our savior.
Yeah.
Yeah. There's a book in what, 20.
take back the day.
It says
We'll try anything.
Natural gas to nuclear.
Yeah.
It'll be small little 250 megawatt nuclear plants.
Yeah, and they have like micro nuclear.
Yeah.
Yeah, sell 250 megawatt.
We have yet to see. Part of what I'm doing here, by the way, if you're trying to understand my perspective on things, it's not that I'm not behind what I'm saying or doing, or I'm not passionate or something like that, but I'm also expected to get funding for things. So I need to put together a package of ideas and a system that looks like something that would be attractive to the NSF and other organizations. So keep that framework in mind as you hear this. So yeah, in terms of greenhouse gas emissions, you see that energy production is the biggest. And then what they do with this pie is they break up that 72%, and you see that 72% is here. And so electricity and heat being the biggest one. Transportation, not something I'm really talking about necessarily in this presentation. And to some degree, manufacturing, construction. But mostly here. We're also the biggest chunk in this one as well. These are pictures you're probably familiar with, the whole climate change thing, the whole smog. Is it? Yeah. It did. Flooding, right. So some of the adaptations that we're going to have to make in the coming years, we're expected to have to adapt our infrastructure like levees and bridges. We're going to have to reinforce buildings. What are we going to do when we're reinforcing these buildings? What other changes can we make as we do that? We're going to have to find ways to recover more quickly from storms, account for agricultural losses. The blooms are happening a little earlier, throwing off pollination schedules, things like that. People are seeing the effects of climate change and they are on the move. I know there's a lot of talk that a lot of the folks that are moving from the South America, Central America, and further north are really climate refugees, so to speak. We have this vicious cycle of permafrost gases that are being released, particularly like in Russia and some of the northern European countries. And people must remain indoors for longer and longer periods as temperatures increase. I don't think we're going to see as I see some of these articles, I don't think we're going to see the end of air conditioning. I think we're only going to see more of it. I know I see a lot of these articles say, oh, well, air conditioning is so bad for the environment, all this, energy and electricity, but it's also a major source of, quality of life, human health, right? Productivity, right? It's not going anywhere.
It's a vicious cycle.
It is.
First we got to take the internet away from all the data centers.
Yeah.
That's small, I'll go run.
That's right. Go play outside, kids. Actually, that's what we should do.
Children in the corn burning the world down.
We're going to power the data centers with kids on stationary bikes.
Like the Matrix and all that. I like
Yeah. All right, so according to the IPCC and all kinds of other scientists and researchers out there, climate or carbon removal is unavoidable as climate dangers grow, right? Has anybody seen what this is? Anybody seen this before? This is a direct air capture setup. So this unit here, what it does is it moves a lot of air through these units here and pulls CO2 out of the air. How many have heard of carbon capture?
Where does it put it?
Just bury it, it's like garbage.
Well, it depends. There's a lot of different technologies out there. Some of it essentially liquefies it and then stores it, which is expensive. There is a technology in Canada where they basically mineralize it into pellets. And then what you can do is store the pellets in ambient air, and then you heat them up, and then that releases the CO2. The end goal is to take the CO2 that's captured and bury it. So it actually, if you, why are you laughing?
On Mars.
Yeah, they bury it. They actually bury it. It's mineralization. So the CO2 actually sticks, it adheres to minerals underground. And I've got a map that shows a couple of places.
It's got stored right next to the uranium market.
Yeah, right.
How energy intensive are these installations?
So the question is, how energy intensive are these installations? Each technology is a little bit different. I'm going to talk about one in particular that's called temperature swing vacuum adsorption. And these companies they all have their proprietary, system, and they don't really like to share a lot of data. But the one piece of information I can tell you, it's a 1.2 to 1 in terms of carbon removal, but not in the good way. So for every 1.2 tons of CO2 that they create, they pull out only one, right? If they use, coal-fired power plants. So they've got to use solar, and they've got to run these things basically nonstop in order for them to actually reduce the amount of carbon in the atmosphere. That's about the only way I can really explain it in terms of energy intensity.
That's another discussion. We'll tell you later.
Okay. All right, so the second goal here is to stop emitting and start removing CO2 from the atmosphere. And I've always thought from the time I heard about this kind of issue that doing this kind of work it should be, and seems like it would just go with also cleaning the air in terms of pollution, right? It just seems like the two things would happen at the same time. For these to work, by the way, the air needs to be filtered coming into it. So like particulate matter, humidity, all that stuff's got to be regulated for these machines to work efficiently. So it always seemed to me like that was that they go hand in hand. So some of the short-term things that have been done would be like this thing called enhanced oil recovery. I had the opportunity to go see one of these sites not too long ago. Basically what this means is they're pumping CO2 into wells where, oil wells, where they can squeeze out just a little bit more oil if they pump CO2 into it and pressurize it, right? And supposedly the CO2 remains in that geologic formation, but we're not real sure yet exactly how that's all working.
Until it gets in the groundwater and gets in the pressure, creates carbonic acid, people get cancer in their cells and everything else.
Could be.
That's assuming they didn't use hydrochloric or sulfuric acid as part of their production enhancements in the well in the first place, and it remains as CO2 instead of turning to hydrogen sulfide gas.
Yeah. Cogen, of course, trying to find lower carbon fuels. And then there's been, since the 70s, direct air capture of carbon dioxide in gas streams for doing like refining oil and capturing methane, natural gas, and stuff like that. So that's been going on for a little while. Long-term direct air capture of ambient air, not in the waste stream of, exhaust stream of a power plant or something like that. And then the big push now is for carbon capture, utilization, and storage. Right? So this is finding a way to use the captured carbon for some kind of economic benefit, and then finally storing it in something. And of course, reforestation, good luck with that. We've been chewing up the Amazon now for, I don't know how many years. I don't think we're gonna, maybe we'll see a day when we reverse that, but who knows. All right, so now we're moving into some of the challenges with the HVAC industry. So we talked, yeah.
So just on that, to that point, there's this whole mythology out there, just plant a tree or something.
Right.
But we're also, at the same time, seeing more fires. So, it's just not a viable strategy.
That's why I put it in the long-term category.
Yeah.
It's not really something where you just go plant a few trees and now you've solved the problem, or made much of a dent. It's something that's got to be approached in a pretty systematic way. And I don't have much knowledge or information on that particular subject. I just know that reforestation is one of the many possible solutions. All right, so some of the challenges of this particular industry, some of this is related to developing countries or places where the infrastructure currently doesn't support the kind of systems that we are well versed in this part of the world. So for instance, structures in the world may not be able to carry the load of needed equipment and or no ground location available. I think of places like India, where and lots of places like in China, where there's just simply no infrastructure for this kind of stuff, and everybody's got a window shaker because there is no big system that sits on the roof that serves the entire building. Of course, we're going to need lots of fan, compressor, and pump power. We have high capital costs, high operating costs. Currently experiencing a lack of parts. That's probably not going to change a whole lot. A lack of technical knowledge, right? This is why we're all here. Maintenance best practices, and of course, the big topic of the day, refrigerant management, right? All right, so I don't think I need to argue this point a whole lot. This is what a lot of the world looks like, a lot of the world. And, scaling is going to produce a lot of efficiency gains.
What city in California is it from?
Yeah. It does kind of remind me of a restaurant I got called to a few years back where it was that, the air conditioning just wasn't working. Tiny little, mom and pop type restaurant, and they had a 2-ton AC, right, for the kitchen, and then that was what they bought the restaurant with, and then they added a 4-ton for the dining area, and that still wasn't enough. So then they added a mini split in the kitchen, and that still wasn't enough. So then they put on a rooftop unit, and that still wasn't enough. Yeah, so actually nothing was coming out of any of the ductwork. None of the supplies were ever connected. That's all it was. That's all it was. Yeah, that's it.
Where was that?
Oh, in just outside of Lansing in one of our suburbs.
And are you saying this is an example of scaling?
Well, it was all going into the cellar, the basement. It's like a cellar. It's not actually connected to the you got to go outside, open the cellar doors, right? And it was all being dumped into there. So it was just like a mold and mildew heaven. Yeah. Yeah. Brilliant. Just absolutely brilliant.
Sean,
Yeah.
is this, what do you mean that this is an example of scaling? Just the
No, I'm saying this is-
proliferation of window units?
This is not an example of scaling.
Oh.
This is what we're seeing all over the world because none of these buildings were built with the infrastructure to make it possible to do a rooftop unit or to have, right, they don't have any of this kind of stuff. And you're not going to take one of these buildings and suddenly, drop a chiller into it, have a whole building air handler or something like that. And the worst part about this is that when these things go bad, what do these people do with them? Right? They just toss them. And I mean, there's stacks and piles of these things when I was in China. And then you just see, like, as the bulldozers pushing them away, just refrigerants going every which way, right? This is the kind of situation that we're dealing with, worldwide. So they say that HVAC is 10% of the world energy use, but I think it's probably closer to 20. I don't have any data to like back that up. It just seems like there's a lot in the world that's going on in terms of air conditioning that we're not really accounting for. And of course, the cooling exacerbates the warming and this, pollution in this vicious circle, right? So we use air conditioning because it's getting hotter outside. The more we use the air conditioning, the hotter it's going to get outside, right? So we've got this problem. So,
Sean, did you ever get any information in automotive, what percent of the energy consumed is the HVAC side of things? Especially like air conditioning, you turn it off because you're running out of gas,
I don't know.
That was the old way. I don't know if anybody ever did that, but, because I gotta listen to the auto guys always tell me that they teach our whole program in one class.
Oh, yeah.
Because auto has to do a section on HVAC, so it's a fun little.
Yeah, because I'm sure all those techs out there have their MVAC certification, right?
Yeah.
Yeah, I don't know. 15%, 25%, that would be my guess. I really have no idea. So I don't know if you're familiar with this, but in Qatar and other places in this region of the world, they are air conditioning the outdoors. This is a mostly soccer arena here, and you can see they've got vents underneath the seats. It's open to the air. I mean, they've got a way to cover it, right? But it's removable.
It's like recent refrigeration.
Yeah, yeah.
Big supermarket.
Evaporative coolers, Dubai maybe, I can't remember. Either way, I mean, we've gotten to the point where we're cooling the outside in certain places of the world, right? All right, so we see here, from the IEA, space cooling is the thing that's increasing, right? And so it kind of goes without saying that heating is, sort of tapering off, right? Again, preaching to the choir here. Buildings, they show this area here as unrealized energy efficiency potential. So we have got a lot of room to make up here. We've got a lot of efficiency gains that we could employ. This was 2010 to 2018 here, and they show that little sliver there of energy saved owing to efficiency. So we certainly have made some gains. However, for every gain it seems that we make, we add more capacity, more electrification, a lot more capacity to our grids. So we're expanding even though we're trying to make things more efficient. So this one here is I find really interesting, and my conclusion with this one is that we are moving indoors. So what this is saying here is this is a linear population growth, right? We've got sort of a linear energy growth here. Our emissions are, kind of maybe linear, hard to say, but our floor area has increased a ton, right? So this tells me that per person, we are adding more space, right? All right, so the secret challenge of the HVAC industry that a lot of other people outside of the industry are not quite as familiar with is refrigerants, right, and their leakage. So some of you are probably aware that we're allowed up to 30% loss depending on the size of the system. So 50 pounds of lost refrigerant would be 27,150 times CO2 equivalent if you're using something like 134A. There are a lot of estimates out there, so I've kind of gathered as many as I could, and those numbers range anywhere from 1 to 6% of total greenhouse gas emissions. That's significant. That's a significant amount of emissions from refrigerant leakage.
30%, like over
A year, yeah,
It's like 35 for industrial sites.
yeah,
I think it's 35, and we had just 36,000 pounds of R22. And they'd be jacking 1,000-pound tanks into that thing. It's like you're allowed 12, 15,000
Yeah.
pounds a year per. Get out of here. Times the world. It's ridiculous.
yeah,
And that's only on systems that are above a certain threshold.
right,
If it has 50 pounds or less, you can hook up a refrigerant bottle like a frickin' IV to the thing and never even look for a leak by code requirements.
correct.
Your customers probably will watch you find the leak from a price standpoint eventually, but
They're trying.
isn't that horrifying?
Yeah.
The people that created the Montreal Protocol are the ones that sell refrigerants, so who cares,
Right.
That's the sad truth of that racket.
Yeah, I remember my first, the first time I went to a site where the whole charge had been lost. It was on MSU's campus, and it was 200 pounds in a chiller that had leaked out from I think it was like a rock hit it or construction crane or something like that hit it, and so we needed to patch it up and fill it. And I remember being like, wow, that was just one chiller at one time. How many more of these happen every day all over the world?
It used to be standard practice to just open it.
Right.
Vent thousands of pounds out.
Yeah.
Recovery's out.
People still do that.
So EPA says supermarkets leak about 25% of their refrigerants annually. According to this person from California, HFCs amount to 4 to 5% of greenhouse gas emissions. So it's somewhere in that 1 to 6% range. And again, we're not accounting for countries all over the world that have no regulations that just dump whatever, whenever. So there's this thing called Project Drawdown. Some of you might be familiar with this. It's they're trying to help.
We had a presentation on it at the Winter Institute
Yeah.
a couple of years ago.
Yeah, that's where I heard about it. Basically trying to find ways to reduce greenhouse gases. They have their 100 strategies for drawdown, right? And I pulled, okay, yeah, you can see it all. I did my best to cut and paste it. I pulled the ones out of their 100 strategies that had to do with buildings. And as you can see here, refrigerant management and alternative refrigerants are the two biggest by a long shot. Smart thermostats and building automation systems are in there. That's kind of nice. And then another one I'm going to point to here is district heating. Have any of you ever heard of this district heating and cooling? You have. Okay. All right. So third and final goal, reduce HVAC impacts through efficiency and refrigerant management, right? So move to things like CO2, ammonia, which I know all of you love, and A2L refrigerants. I really also think we need to reconsider A2Ls and really move in that direction as well. But that's not the point of my presentation today. Of course, we need to move to renewable energy. It just seems like it would go hand in hand, especially with solar power and air conditioning. Sun's out, gets hot out. Seems like the two could be tied in a little bit closer together. I really think worldwide we need to reconsider our HVAC infrastructure. Again, this is not sustainable. This is not going to make sense long term. And I think we can do a better job of implementing things like thermal storage. All right, so the 3 goals, just to sum this section here: clean the air, stop emitting and start removing CO2, and then start doing things in the HVAC industry, buildings in general, making them more efficient, running more efficiently, et cetera. All right, so CO2 heat pumps and AC, refrigeration, domestic hot water systems. Any of you familiar with, I know we talked a little bit about CO2 systems. Anybody else work with any, have any experience with CO2? I recently went to a training through RETA, Refrigeration Engineers and Technicians Association, and got certified as a ammonia CO2 cascade technician. We got to work on a couple machines. I have some basic working knowledge of how it all goes. I've been considering acquiring a CO2 system to kind of goof around with and try to understand a little bit better. In the CO2 refrigeration world, you've got the subcritical cycle, and then you've got a transcritical cycle. So as you go into transcritical, the temperature-pressure relationship starts to break down, and they're no longer connected. The subcritical cycle runs a little bit more efficiently, has a better COP. However, down here in your evaporation phase, if your pressures aren't just right, you can end up with dry ice. And now you've pretty much destroyed your system. So that's no good. Transcritical is great because you stay in a vapor phase the whole time. Your COP drops, and you lose a good chunk of your cone here in your enthalpy diagram. You lose quite a bit of it in order to stay transcritical. So there's been some technological improvements in subcritical. Danfoss has this multi-ejector system, which is pretty cool. And then there's a company called Sealy that does a dew point cooler that is able to keep subcritical cycles going even at 40 degrees Celsius, which is like India temperatures. Probably the best way to do CO2 air conditioning and refrigeration is to do some kind of booster or combined cycle so that you can maximize the time that your refrigerant is spending inside the dome. So this kind of system typically works well at larger scales like grocery stores or mixed use where you've got like high, medium, low temperature cooling needs. I think a lot of them either employ a charge compensator or could benefit from one. They can certainly use wastewater for heating. In fact, that makes a lot of sense because you've got high condenser discharge temperatures. Thermal storage, ice storage, right? CO2 is, you can make dry ice from it. It also gets really cold if you do cascade. I was working just a few weeks ago, this was in Kansas, in a freezer unit that was minus 40. So you got to put on all this PPE and go in there and adjust the ejectors and all kinds of stuff. Is pretty fun. For a short time. I wouldn't want to do that for a job, though. It smells like pee everywhere. Right? Ammonia? It's awful, even when it's not leaking. CO2 is also, could be considered a utilization in that carbon capture, utilization, and storage economy. Some of the cons, though, of working with CO2 is the high working pressure. It easily gets over 1,000 to almost 1,600 PSI. You've got to use thicker gauge piping, including stainless steel. It does have an asphyxiation risk. CO2 is heavier than air, so there's some concerns there. You're going to need more sensors and things like that. And transcritical cycle has a little bit lower COP, so it's not quite as efficient, which is the main reason why CO2, having been one of the original refrigerants when air conditioning and refrigeration was invented, became outmoded because we have more efficient refrigerants. They just happen to be not so great for our environment. This is a system here that is made by a company called Link, and this is a water heating heat pump using CO2, and this company is right now is considering offering me one of their units to install over at MSU to do some testing on. And we're thinking about maybe cascading this with an air conditioning setup and seeing what we can make work with it. But you'll notice here how much, this is transcritical, but how much of it actually does sit inside that dome there. So you only get a little bit of losses in order to keep it transcritical. So it does work quite efficiently. All right, so moving on, natural gas pipelines. I know, Peter, you were talking earlier about natural gas being leaky. At a minimum, it leaks 1 to 3%. Some estimates have it closer to 10.
Are those numbers production numbers or post-production?
This is just transit,
Okay.
just transit through the pipelines.
Because the numbers for production
Oh, yeah.
estimates are astronomical
Yeah.
in comparison.
It's like 40% or something like that.
Yeah.
Yeah, it's really bad. Of course, there's a indoor air quality risk from leaks. I know I have natural gas in my house. How many of you have a natural gas furnace? Yeah. I mean, not that I'm that worried about it, that it's super dangerous, but it is a risk. So it does have that potential for combustion. I think what we're going to start seeing, because there's really this push, and it's pretty much worldwide, this push for electrification and moving to heat pumps. I think we're going to see a lot of decommissioning of these pipelines, and they do have a potential for reuse as CO2 pipelines. In fact, right now in the United States, I just pulled this from an article here, Americans are unaware of carbon capture and sequestration technology. These are the carbon capture sites and pipelines that exist today. Here are proposed CO2 only pipelines. Some of these are going to be or have been converted from natural gas. I'm familiar with these two here and got to visit one of those not too long ago. This is one right now that's there's a lot of political fighting going on about this. There's people on both sides of the environmental issue trying to decide whether or not they think this is a good idea. Certainly there's some safety issues. Again, CO2 heavier than air. If it does leak, you're going to get pockets where you could walk into a zone, and become asphyxiated. So there's definitely some concerns here, and I certainly don't want to gloss over those. But this is probably the largest and most comprehensive pipeline for CO2 that's being proposed today, at least in the United States. So where does CO2 come from at the moment? Pre-combustion for natural gas. So it's carbon positive because it only captures about 60% of it. Oil refinery flue gas recovery, still a very carbon positive activity. Enhanced oil recovery, it's carbon not sure yet. It's not been done long enough. There's not a lot of data out there to know for sure exactly how that's all working. The kind of places where oil exists and the mineral structures that are in there are not necessarily suitable for carbon storage. The industrial fermentation process, carbon neutral only if powered by renewables. And then there's two kinds of direct air capture. One of those is the strong-based sorbents that go into exhaust stacks for like industrial processes. And then the other is what I'm talking about, which is the weak-based sorbents in ambient air. And it can only be carbon positive if powered by renewables. Otherwise, it's completely pointless. So this is an industrial fermentation site for CO2. So they're taking waste agricultural products. So whatever's left over from corn, beans, that kind of thing, dump it into this reformer here. It ferments, and then this long pipe right here pulls off the top and is basically pure CO2. They run that through a series of massive compressors. So this is a 4160 volt unit here, right? And here's their, here's where their compressors are, and and then sends it out into the into the pipeline for enhanced oil recovery. The pipeline is 14 miles long. Very interesting to see. Yeah.
How many gallons did they say, what's it capable of on average when it's pumped, does this come up?
You know what? I might have it in some of my photos because I got to take a picture of the control panel and all that kind of stuff, but I don't know off the top of my head.
Then, you were saying the solar was, you're talking about adsorption or absorption?
Adsorption. Yeah, adsorption, essentially, it's clinging to a substrate,
Right.
more or less.
And what, do they have an idea of what substrate they're thinking about going, besides like coal or something?
Substrates range from these kind of like mineral powders all the way to what they call metal organic frameworks. The hub of metal organic framework research is in Chicago, believe it or not.
That sounds like it could poison some more water in Michigan.
Well, what it is, these metal organic frameworks, what they do is they attach this powder or whatever to something that basically looks like a filter, like what we would be used to saying is a filter. And then the CO2 gets stuck to it as air moves through it. And then they put it through this temperature vacuum swing adsorption process where they actually desorb the CO2 from this filter through vacuum and heat. So the filter, the framework, that sorbent material is stable. It doesn't go anywhere, and it's rechargeable up to like 5,000 charges or something like that.
So it's like a liquid too, so it's almost like a
There are amine-based liquids as well, but the one that I've been looking at for the most part is it's all solids.
Similar to water softener.
Perhaps, yeah. So yeah, this is the basic process here. Fans draw in the air. The air is pushed through this filtration system, and the CO2 concentration is lowered. And then the filter is heated and put under vacuum, and then stored somehow. Yeah, so here's another unit.
that costs a lot of money.
Oh, yeah, it's totally ridiculous. And this is what they look like, more or less on the inside. Some of them have filters that are more like just a single film, and then these ones here are more of like this grid type framework. There's other ones that actually drip water through them for one reason or another.
Yeah, Sean,
Yeah.
what dangers to birds are posed by that kind of mechanism?
I have no answer. Most of these air capture installations really are not sharing any information.
Right, I mean, because that was the argument against wind turbines.
Yeah, yeah.
Those blades move a hell of a lot faster than the turbine.
Yeah, I don't know. I think you just put a no birds allowed sign and
Just get more varmints out there
Yeah.
cleaning the mess up.
So actually, part of the problem with wind turbines and birds is the slow speed the blades move at. Birds are actually exceptionally good at avoiding things that are moving at high speeds. So as long as they don't literally get sucked into
Yeah.
the fan.
I mean they got
They
little
also get
covers.
killed by the
No, we don't. Not this one.
Just by hitting vehicles themselves. They are moving at.
So you see, I wasn't joking about Maloa, right? We're moving a lot of air to do this.
That's nothing on the grand scale,
Now,
What, I mean, have they talked about just regulating the biggest producers and forcing them to build these structures? 'Cause that's, I mean, you'd almost have to localize something like that. You can do nothing with the dilution rates anywhere else. Like they should all be forced to at least start testing it.
You would think, yeah. No, it's totally separate companies that engage in this kind of activity, not connected to any oil, gas companies, nothing like that. Not that I'm aware of. Oil and gas really, really pushes for that direct air capture on their own exhaust and flue stacks, right? They love that because that makes them look green, even though it's really not particularly,
Well, and then they can fudge the numbers.
right.
Well, if they also have higher concentrations, it's easier to pull it out at higher concentrations, I would think.
Yes, it is. It is. All right, so these temperature vacuum swing adsorption processes, there's a bunch of different ones out there, but more or less they all operate around the same kind of concept. Air, somewhere between 50 and 500 CFM, not anything too different than what we're used to seeing in the HVAC world, moves across a metal organic framework or some other kind of sorbent type material and captures the CO2 particles. And then it's removed by placing it under a vacuum, usually about 5 kPa, negative 5 kPa, and then heated to 80, 100 degrees Celsius. And then it needs to be connected to some kind of utilization or sequestration pipeline for economic competitiveness, right? What do you do with the CO2 after you captured it? You're literally not creating any product, right? You pulled the CO2 out, that's great. Congratulations, right? This is a, market economies, capitalist economy. You've got to have something to make or sell. The only thing that they can make or sell out of this is carbon credits, right? And again, that 1.2 particles added to the atmosphere for every 1 particle removed when using something like coal power, right? So you've got to find another way to operate this stuff. Here's an example for you. This one's in Canada as well. When I read about this one, the inventor of this literally said, I took an air handler and I converted it to this direct air capture system. Climeworks, I personally, yeah, go ahead.
Roll back a few slides. Negative 5 kilopascals, that's not even an inch of mercury, is it? That's a really light vacuum.
Correct.
Okay.
Yeah. So I think Climeworks is in, I don't know, Iceland, something like that, somewhere in Scandinavia, something I can't remember. I think that they probably have the best secret sauce. Don't know exactly what that secret sauce is, but it seems like they're doing the best job. They seem the most organized, and they seem to have the right kind of experts working on the job. Some of these other companies, a lot of smoke and mirrors. This one seems to be about as forthright as you can get. So I just want to point out with this one here that they're saying that this unit, right? This is just this one piece of that big array that you saw, does 50 tons of CO2 a year. Okay. This is just some more graphics from their website explaining what they do. So again, there's that 80 to 100 C temperature to release the CO2.
So,
Correct. Ton of energy.
so
Yeah.
in this process, obviously we're moving the air, grabbing the CO2. Do we shut down that unit while we are breaking the CO2 loose from the system? Can we break the CO2 loose while we're still flowing air across it? Is this a manual, go grab the filter and throw it in the oven?
Yes to all of it. So yeah, to summarize what you were saying is, can these direct air capture systems, can they run continuously while they're also removing the CO2 from this substrate, right? And the answer to that is yes, all of it. It just makes it more complicated. So the Climeworks system literally shuts down that air handler, does the TVSA process, right, and then turns it back on again, and goes back to the adsorption process. There's some professor out in Arizona somewhere who's got a system where the sorbent material drops down into a separate vacuum chamber, and then another one is replaced with it, so it never shuts off. right? So you can do all that kind of stuff.
On the units that do shut off, what's the duty cycle look like?
They run anywhere from 15 to 45 minutes, and then the capture process takes 10 to 20 minutes. It's fairly short. And every time I find a new article about this process, they found ways to decrease the time. Really, it's availability of heat. If they just have instant heat, that makes the process a lot quicker.
It's a research in using the CO2 for capturing welding gas, the MIG welders, use a lot of CO2 gas.
That CO2 argon.
Yeah.
Yeah?
We just need to weld more.
Right. Yeah.
Well, for the planet.
So this is, I think you can see here, Michigan is literally covered. A good chunk of Indiana, Ohio, Pennsylvania, and there's a lot of places out in the ocean where it looks like we can do subterranean geological mineralization, where you're basically storing CO2 long term. It actually solidifies into the rocks. I don't have a lot of information on that particular topic.
We've been dumping so much CO2 in Indiana right there that, you know, maybe they're just getting used to it after a while. Maybe the earth can just absorb it.
Yeah.
Absorb it.
Yeah. So some of the other utilizations you're all familiar with, carbonated beverages, of course, concrete production, plastics, greenhouses use CO2, of course, pharmaceuticals, big consumer of CO2, lots of chemical industrial processes, dry ice, right? And we can certainly do more in the way of dry ice storage if we're trying to utilize CO2. And one that always kind of throws me off is jet fuel. So we're going to capture the carbon, turn it into jet fuel, and then just put it right back again.
Dry ice is the same thing, though. I mean, dry ice just sublimates the air, but I guess you could capture it, but then where do you put it?
Well, I'm getting to that.
Oh.
All right, so right now a carbon credit goes anywhere from $40 to $80 a ton. It's gone as low as 10, 20 bucks a ton, all the way up to, I think the highest ever was like 120, something like that. Direct air capture, like what you're seeing here, nobody really knows because these companies, they don't want to share their secret sauce. But the guesses are that it's somewhere between $300 and $600 a ton. So not great, right? So they're not making a profit off this. What they're doing is, you know, basically guilting companies into buying their carbon credits knowing that it's clean, right? That's the way I see it, at least. So how do you bring the price down? Well, economies of scale. The more of these that you do, the cheaper it's going to be to make, you know, produce and build them and deploy them. And my particular area of interest is overlapping processes. We're moving a lot of air here. There are so many processes all over the world that move a lot of air. Just recently, just like in the last few months, this is HEMFC is a kind of a hydrogen fuel cell. They were trying to get it to work for automotive purposes, and it kept failing because it was getting clogged with CO2. And then they realized, wait a second, this thing is really good at capturing CO2. And the amazing thing about it is that they're moving air at just 0.07 CFM through this fuel cell. So it doesn't even take a lot of energy to pull this CO2 out of the system. And then all you got to do is put a little electric charge through the fuel cell, and it releases the CO2. So that's one I'm really interested in having a look at. But this paper was just released. The global carbon credit market, $850 billion a year, right? So this is not a small industry, right? There are people who pay a lot of money to be in this game. Now something to consider. This article here from 2016, one of their conclusions, overall, it is striking that the cost of running the fans for all buildings is at or just above 50% of the total HVAC operating cost. We are moving a lot of air. Are you seeing where I'm going with this? Yeah. So residential fan power is about 25% of total HVAC power consumption, roughly. Lots of industrial processes require moving a lot of air. Parking garages, underground parking garages. I don't know if you've ever seen air handlers for those. I've been in a couple. They're massive. High-rise buildings, of course, shopping centers, commercial refrigeration, which also has some use for dry ice. All these areas have increased concentrations of ambient CO2, right? Buildings, right? Buildings where people are breathing have increased concentrations of CO2 compared to just sucking air from the outside in the middle of nowhere, right? So there's been a very, very small amount of research done into what I'm talking about here. And so far, there was a paper in 2015, and then this paper from 2019, where basically they took did some simulations and integrated TVSA into an air handler for like a residential application. And their conclusion is right down here at the bottom. High energy efficiency capture device in buildings merits attention in the exploration of the possibility of approaching negative carbon buildings. Okay? All right, good enough. So I'm suggesting that not only do we overlap the moving of a lot of air in these two systems, that we capture carbon from buildings rather than just from someplace out in the middle of nowhere, but that we also overlap the temperature vacuum swing adsorption process into the vapor compression cycle or some other part of our HVAC processes. Because the adsorption process likes roughly ambient temperatures like what we like to live in. And the desorption process likes to be at about an 80 to 100 degrees C temperature, which is for subcritical CO2, that's its sweet spot. So why not just overlap the two, right? So another thing that you could do, and this one's maybe a little bit more pie in the sky, but as you're capturing that carbon, you can integrate it right into your refrigeration cycle, right? So depending on whether or not you need to do heating or cooling, rather than doing something like a charge compensator or a receiver, you simply just dump it, right? Send it to the pipeline, and every time you do that, you're making a little bit of money, right? So if you're capturing carbon and it's on top of a building or related to some kind of like, campus or something like that, every time you collect a little bit of carbon dioxide, dump it, or keep it for a refrigeration process or a heating process. All right, so what if direct air capture and CO2 refrigeration were basically overlapped, combined in the same pipeline? So DAC needs a lot of air, needs it to be filtered and dehumidified. We have lots of air too. Needs high CO2 concentrations. We have high CO2 concentrations, and if we can lower the CO2 concentrations in buildings, I think we're doing a good thing for people, right? Needs steam or dry air at 100 degrees C to release from the sorbent, and it just happens to be that HVAC, we're really great at making steam. We're really great at utilizing heat. DAC provides an endless stream of CO2. We can use CO2 as a refrigerant. Nice overlap. Reduces the worst of climate impacts, so they say. And if we were to integrate something like this, we may see an improved quality of life. If we're moving a lot of air, right, even more than maybe what we might consider efficient nowadays, we can filter the air at a faster rate. Plenty of rooftops globally, lots of clients for this technology. We don't have to go and put it out in the middle of nowhere somewhere. And then I think with something like this, you have the ability to justify something like displacement ventilation and other high air exchange dilution strategies. Yeah, maybe it's not efficient on its face, but if you already need to move a lot of air anyway, why not just do it? So DAC needs renewable energy to become carbon negative. And we, as an HVAC industry, need to address the vicious cycle that is using energy to do cooling, only to heat the planet worse. So how can renewables fit into this? So it's critical for DAC to be as carbon neutral as possible. Highest cooling load is at sunny times of day, as you're probably aware. Heating and cooling storage, so either just hot water, dry ice, that kind of thing, now becomes possible with CO2. Solar thermal might be able to be included easily in something like this. And the more that we scale up these systems, the more that we're increasing the efficiency, AKA removing all the window shaders. So another way that we can scale this even bigger and reduce the safety concerns with CO2, do you want a direct air capture and CO2 unit on every roof all over the place, especially in residential? I don't know. But in densely populated urban areas, and I'm thinking places like India, China, really densely populated areas, something like district heating and cooling might make a lot of sense. So now you've got these complicated CO2 heat pump systems that have direct air capture on them. And instead of creating this massive infrastructure to put these things all over every building, you've got some central plant somewhere where you can also find other utilizations for CO2. Beverage bottling, dry ice, greenhouses, right? Who knows? They say that district cooling systems consume 35% and 20% less electricity as compared to traditional air-cooled air conditioning systems and individual water-cooled air conditioning systems using cooling towers. It seems to me like scaling, the more you scale up, the better you get. Copenhagen, Denmark is the global standout in DHC. 98% of heating demand with the world's largest district system fueled with waste heat from coal-fired power plants and waste-to-energy plants, right? I'm sure that they are looking for ways to get rid of the coal and gas plants, and this might be a nice transition for them. So they say that we need to remove 10 gigatons per year by 2050, right, to stay at that 1.5 degrees of cooling. So currently in the atmosphere, we have 3,210 gigatons of CO2. 1 gigaton is a billion metric tons. There's roughly 6 million commercial buildings in the USA. It's nearly impossible to find out how many buildings and eligible buildings are, in existence worldwide. So I just kind of took a look at the United States. So if we just threw one Arctic fox on every commercial building, that's 0.3 gigatons. If we looked at the entire eligible building stock in the United States, now we're at 5.5 gigatons. We're halfway there, right? Is that a reasonable estimate? Is this even close? Not really. These are like the most rough numbers ever. But I think it's at least indicative that we could possibly, this is maybe a solution. It's at least worth doing a dissertation on. 200 million buildings would be needed to run one Arctic fox to hit that 10 gigaton per year load. Can we do 200 million buildings, or can we serve 200 million buildings? Is that a reasonable thing to consider? Can we scale that up? What's that? If we can find parts. All right, so there's a lot of different variations. For instance, rooftop units could be converted and replaced, connected to the CO2 pipeline in some manner. Rural areas might utilize some kind of like tank storage, and then when the tank gets full, they can sell that. Somebody comes pick it up. Cities might have district heating and cooling capability or some sharing of power, cooling, and I think we need to consider, I probably will get some pushback on this, but I think we really need to consider something like district ventilation as well. If we are expanding the amount of living space that we're living in, if we're moving indoors, yeah, I realize it's probably not the most efficient thing to do. It's a lot more efficient to move water around. But imagine how many, is someplace in Delhi, India really going to be doing, filter changes every 4 months? And what does that look like? Can we scale up the filtration of air to the point where we can literally serve air, clean ventilated air to largely populated areas? Probably a little pie in the sky. It's biodome, man. Yeah.
Two quick.
Yeah.
Is the DAC you're talking about, is that the version of carbon capture that requires specific temperatures and humidity in the air being processed, or is that unimportant for this?
No, it does have a temperature range, and it does have a humidity range, but it's not, it's not that critical, right? It does operate better in lower temperatures. That's why you see this thing in Iceland and things like that, Canada. Hmm. But if you're combining that with a heat pump cycle, right, and you're able to, put an evaporator on it, something like that, well, now you're talking.
Next question, is there any delta T across the CO2 absorption process?
No. There's a lot of pressure drop. Yeah, let's see here. So yeah, you can do booster, cascade, hot water systems, dry ice storage, steam, secondary heat transfer. I would even think, again, this is probably a little bit, fantasy. We could do something like an on-demand system where you've just got a system that's just ready to go, no charge on it, and you decide it's time to run this machine, and so you're connected to the pipeline, you charge it on the fly, run the machine, and then dump the charge back into the grid, right, into the CO2 pipeline.
You know what we can do? We can get this built into a mask, and we all wear masks the rest of our lives. Save the world.
One here and one here.
Right there.
Just a general possible way to phase something like this. I'm kind of interested in doing like a proof of concept where we integrate a sorbent into the air handlers and use condenser and evaporator for this temperature vacuum swing absorption process. Not too far off from what other people have already done. Phase 2 would be design the actual CO2 system and then start capturing the carbon, integrating it with the receiver or charge compensator or something like that, and discharge it to the CO2 pipeline. Of course, we're going to have to address oil return issues. I'm not sure how that's going to work in a pipeline. That company that is interested in supplying that CO2 water heating unit, I have talked to the engineer about this, and he seems to think that doing something like this here in phase 2 would work. He didn't, again, engineer though, so who knows. Phase 3 would be integrating an air filter with the sorbent media, making it actually just one single unit rather than two separate processes. And then I think phase 4 might be doing something like integrating this concept into district heating and cooling. Let's see. Yep, last 2 slides.
Okay, yeah, they're outside.
Okay.
Yeah.
So the CO2 economy needs a velocity of money boost with more participants capturing and using CO2. This industry is not going to really do anything or take off. This whole concept of capturing carbon and using this carbon economy is not helpful if there's only this small number of players. Carbon capture costs can be offset by customers paying for the air conditioning, right? So we are already paying money to do air conditioning. The process of doing carbon capture on top of that is not going to increase the cost that dramatically that you wouldn't be able to offset your costs by selling that carbon back. Let's see here. Obviously, new jobs, installing, maintaining, manufacturing components, all that kind of stuff. Provides an immediate benefit, healthier people, and possibly a major reduction in the high global warming potential refrigerants that we use today. Additionally, there is something that was passed back in 2020, Section 45Q of HR 133, gives you a $20 per ton tax credit for doing carbon capture. All right, so in summary, thanks for hanging with me for all of this. We can address global air quality issues for quality of life and economic resilience. I think it's incumbent upon us to really do that. Medical expenses and medical costs are only going to rise. We can reduce the negative impacts of HVAC use through energy efficiency and refrigerant management, nothing you didn't already know. Remove CO2 from the atmosphere of a rate of 10 gigatons per year. It does seem like it's a hard target to hit, but what do? Do we give up or do we try to do something about it? These goals can be achieved by overlapping the need for moving a lot of air in carbon capture and HVAC. Switching to CO2 refrigerants helps reduce carbon capture utilization and storage costs and mitigates our global warming potential. Scaling to district level distribution increases efficiency and improves safety. That's what I got for you.
Good job.